Hi guys, sorry I wasn't there. Just
Hi, Prasun. Thank you. At least you are available.
why are we on this perceptron problem? I mean, the question is like the codes are really down below, right? Why are we- This is the loss function, no? Uh, we what we do is when we have a loss function, see if it is MSC or say absolute error, no? Then we try to do through gradient descent in all the problems we use gradient descent. And what the gradient descent does is we differentiate it partially with respect to the weights. Like if it is theta, then theta, then otherwise it's W. So here it's W probably. So what we do is when we differentiate it with theta or W, the term which is inside the brackets, right, that will be differentiated first, and then the term with that theta in itself. So when we differentiate that term, like for the chain rule, when we differentiate that, there will be an additional x in it, because ultimately the theta is multiplied with x, right? Yeah, but what we remember is just a moment, I should share screen. Uh, yes. Can you guys see? I mean, like my screen has been shared, right? Okay. No, this is mine, right? You can see a black screen where perceptron codes. Hello.
Yes, 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 yes.
Okay. Okay. This is very confusing. Let's okay. Okay. So a simple loss function is um say mean square error. What we will do for mean square error, we will have this. So this is y minus y hat, and it is square. This half is just to make our jobs easy later on. Okay. So this is the error. Y is the actual value. Y hat is our predicted value, and it will always be different from what is actual y, because it is the initial model when we are iterating through the weights. So y minus y hat, same is with perceptron. If we, I mean, did I break the code? Why is it not running? What did I do? Okay. So here it is. This j is basically maximizing either this or it will be zero. Why? Because in last session probably I told you about these identity functions, right? Identity functions. what it did, it takes either maximum of 0 or some other function, y and y and x. Where did it come from, y and x? If we differentiate this with respect to theta, and this particular term is actually theta transpose x. I hope you guys are listening still. If there's anything you can't relate, please let me know. So this is the loss function. This is the basic loss function. We expand this y hat using this. Okay, yeah, y cap is theta transpose x, and this is square. Okay, once we differentiate
Why
it with,
1 by 2 SH?
sorry,
Why 1 by 2 if we are putting inside before it?
uh, to make our work easy, when we differentiate this whole term, no, the
Mm-hmm.
2 will come in the beginning. We remember the differentiation, no? When
Yeah,
x
yeah.
square, it will become 2x,
Mm-hmm.
right?
Yes.
So what we do is, to make our jobs easy, we could 1 by 2 before that particular, uh, what you say, this function, so that when the 2 is introduced after differentiation, it gets cancelled out. Okay, so you will see it happening in most of uh, machine learning theory. So it's only a generalization. We are not really worried about the precision. We only need generalization, and whichever way we get our work done easier, we do that. It doesn't matter why we do that. Okay. So what will happen here if I differentiate it with theta? First, I will write down this whole function as such. Okay. So 2 I got, then y minus theta transpose x. Okay. Now what we'll do, we will differentiate this entire term inside this bracket. So what will happen is, this term doesn't have a theta, so this is as good as a constant. This term has a theta, but it is negative. So when we differentiate it, what will happen? Minus theta, it will become x. Okay. So this is basically y minus theta transpose x into minus x. So every other term, when we sorry, uh, y minus theta x minus x. So basically, when we do yx, so when you multiply minus y x, and this is theta x. And now for perceptron, what is a perceptron? It is a single layer, right? A single neuron, right? So for this single neuron, we have the function like this: w naught plus w1 x1. Okay, so this is the bias, w is the bias, and w1 is the weight for the input, actual weight for the input, which we need to iterate. So theta is part of this. If you write it theta, then theta naught, and theta 1 x1, theta 1 x1. I hope this is clear. I mean, get it again. Theta naught plus theta 1 x1. Okay, so this is the same thing. So theta 1, when we write it, it is either 0 or 1. We take only these two values, either 0 or 1. So now what we have here is a um, sorry, the activation function used in perceptron is 1 if z is greater than 0. So for this they are saying,
Is our Z is activation function here?
yeah, so if the point is like this and the point is like this, if the point lies here, then it is plus 1. If the point is here, then it is minus 1. This is what is saying. Yeah? This is what it means, right? Activation function. This is what it's trying to say. If the perceptron gets the value on this side of the decision boundary, then it is plus 1. Otherwise, it is minus 1. Are we?
Yes, yes.
Yes, no? Okay. So, and now when we are predicting, we want to maximize our cost function, the loss function we have to minimize. So, in both ways, we will do this sum of all the losses, right? And the losses come out to be this yx plus theta x. Yx, um, why is this there? Z, if z is differentiated with w, then it will have.
This cost function or cost function is same or different? Because this is telling cost, compute the cost function j equal to 1 by x sigma max 0 minus yxw. What is there? That is the cost function.
Yes, it is a cost function. Z is basically our line, that the decision boundary. This is wx plus b. This is z,
Okay.
right? And y is our variable. Like this is y. Okay, this point is y, actual point. If I'm predicting and I get it here, then this is y hat, right?
This boundary is a wx, huh? You mean to say?
No, it is wx plus b.
Wx plus b.
Yeah, this is wx plus b. I think it will be better if we remember the svm concept. How many of you are good with it? I mean, still remember the svm concept?
Wx plus b, that I remember now.
In svm also, what we used to do is, whenever see, svm is basically, inherently it will classify only two classes. So it's a binary classifier for svm, right? So if any point lies on right hand side, we assume that it is a plus point. If any point lies on the left hand side, we assume that it's minus 1, right? This is what svm does, and the same is being done here. This formula gives us a simple linear separable uh, classifying boundary. So if the points are like these, the one point is like this, one point is like this, and there are other points which are linearly separable, then only we can do a linear classification like this. Then what we will say, the result is 1 if the z, this value is greater than 0. Okay, if it has been like a support vector machine, then for this margin, this will, for these points it will be 1. If you remember, do you guys remember, the z was 1 for this points lying on the margin of this support vector. And like this also, if it lies on here, it will be minus 1, and otherwise it is greater than 1 or greater than minus 1. Do you guys remember this? I mean, Of course, you can check with SVM. SVM binary plots. See, this is the separating hyperplane which I was talking about. This is wx plus b. Okay, here the slope is positive. Wx, the w is positive, and here the w is negative. Okay, this is our support vectors which lie on the margin. And in support vector machine, we rely on maximizing the width of the margin to find such a hyperplane where we can maximize the margin, the gap between the these two lines where the support vector lies. Any vector, the least distance from these vector to the separating hyperplane is the margin. Okay. Now what we have here is yes. So these points are like, if this, we have to say this is A. For Z greater than 0, we will have 1, and for Z less than 0, we will have -1. Okay, so these are A. Now, given the predictions on all examples, you can also compute cost of J. The cost function is nothing but the formula here, what we derived here, minus yx plus theta x. This is what are the terms like. If you have to define it in terms of a function, what do we have here? Y, x, theta. Okay, these are the three terms which we have. Okay, we have to make a function with all these three terms. I hope you guys haven't slept. I'm like very slow, but please bear
Hmm.
with me, right? So we have this function with y, x, and theta. Whichever whichever equation you see here is nothing but the cost function, and we define it like this. Okay, if you want to add a Lagrangian function, then you will add a Lagrangian as well, right? If it is a Lagrangian function, then you will add a alpha as well. Nothing else. There's nothing. It's not a big thing. It's just how you solve the optimization. What is optimization? Optimization is just the maximum value for a given function within the constraint of its domain. Like y cannot go out of its domain. If it is 1 and a -1, it will have to stay within 1 and -1. X, if it is real number, all real numbers, it cannot go to the domain of a complex number. It will have to stay within the domain of a real number only. Theta, if the theta has a domain of 1 to 10, or say -10 to 10, it will not go beyond that, right? So all this function has a constraint. Sorry.
Sorry, sorry, Ji, my mom interview.
Okay. So I hope you guys can still follow what I'm saying. I mean, have you guys understood this already? Because this is nothing but just a term written in terms of these parameters. Nothing else. See, maximum either 0 or these terms multiplied.
Yeah, Prasun, actually, I'm sorry. This minus y x w is the thing that's confusing actually. Uh, it will be, what will be that actually y is the target and x is the our current one state, right? Current value.
No, X is the data.
X is the data.
XW is the current prediction. Y
Yeah.
is the actual target.
Yeah. So we are multiplying these means what's the meaning in multiplying these two?
Actually, what you're asking is the same thing which I asked myself 2 years back when we were doing the clause optimization. See, this has no importance in itself. Why I am trying to tell you about support vector machine is because I might find this somewhere. See, y fx is equal to 1. Support vectors on the boundary. See, this fx is nothing but xw.
Mm, okay. Okay.
just know that this entire optimization stems from the very understanding that if, for example, I have a term on the plus side. This is a plus side, Manoj. Okay,
Yeah.
we have every point here as plus, and all those points which lie on the margin is plus one. Okay, we just take this information and we keep it. We believe it hardcore. Okay, and then we have other points which are negative minus one if it lies on this margin, and otherwise negative in this entire region. Okay, so if I generalize my SVM function hyperplane, okay, if I have to generalize the function, optimization function, then what do I do? I write it this: y into fx is equal to 1. Now, what will happen if I take this as a general function of SVM? What will happen is y is plus 1 if it's on this side,
Yeah.
eh, and the fx, the function fx is wx plus b. Okay, if it is wx plus b and it is positive, then positive into positive will always become positive, and it is 1 because it is on the margin. Okay, and if it is on the left hand side, the target itself is minus 1, and wx plus b is also minus 1. Okay, because it is on the left hand side. Okay, any point on the left hand side will be minus 1. This we can actually derive. You guys have how many of you are from this done crash course of joint engineering entrance test during your college days? You remember uh, when we used to what we used to do is we used to have these coordinates like two axis coordinates. Okay, and there's a pointer. The teacher used to ask what will happen if this is x and y, what will be the new coordinate system if the coordinate, if the Cartesian is rotated by an angle theta. Have you done in one of these problems?
Me no.
Okay, so what happens here is if this point is plus and like what we have with this is plus, if you rotate this Cartesian itself, it will give you a rotation matrix. It will be cos of theta minus sine of theta. Oh, this is so hard to write with the finger on a trackpad, no? I hope this is making sense to you. This is cos theta. That was minus sine theta. Then sine theta. This is cos theta. Okay. So in order to get this new value for xy, I'll have to multiply this with cos theta minus sine theta, cos theta. This matrix is a rotation matrix, simply put. Okay, and if I rotate this at 90 degrees, then it is simply cos 90 is cos 90 is 1, I guess, right? Sine 90, sorry, cos 90 is 0 or 1. What is it? Hello?
Uh, Cos 90. I don't know. Anyone knows cos 90? Otherwise, I will search it on the Google.
Why would you have to search it? Just remember now. What is it? Try to remember. Like if
Zero.
you draw this sine function, this is 0, and like this is a sine function. Always remember like this, and this is our cost function. Okay, so sine 0. This is 1 by like pi by 2. This is pi by 2, 90. So what is cos at 90? Cos is 0, right? And sine theta, sine at 90 is 1. Okay, So cos at 90 0, this is 1, this is minus 1. So if we turn the table, like if we turn the axis entirely by 90 degrees, then I'll have to multiply it with 0, minus 1, 1 and 0, simply put. And when we do that, we will find that this guy is like this guy will turn negative, and this guy will turn positive, right?
Okay, yeah.
You can imagine it, right? If I just, if the x-axis like this and this is like that, you will, how is it like, okay, let me multiply this. This is the vector. Okay, what will be happen, this is 0, this is multiplied with minus y. Okay, so this is minus y, and what will happen with this? This is x and 0, this is x and 0. So the value is entirely different. Now it is the x is what is minus y, and y is actually x, right? Sorry, the notation is wrong. To represent a vector in Cartesian coordinates, we have to write like this. Okay, so this is what will happen. And if I take a vector of this is x square plus y square under root, this is y square.
Yeah, that time was out, no? So can you please share the screen again?
Yes, doing it here. Okay, where did I lose you guys? I mean, this is, I know this is kind of a boring stuff which I'm doing right now, but you will ultimately get it. You can see the screen, right? So
Yeah, yeah,
if this is vector xy, right, Manoj?
yeah,
Hello?
yeah,
Hello,
yeah, yeah. I
yes,
was not
just
muted.
Okay. No, please don't mute it. I mean, unless until you have a very noisy child around, we can keep the mic open so that I can interact. I don't really understand if you are there participating, and I need a participation constantly. Okay.
Okay.
So this is the vector xy, original vector x and y, abscissa, ordinate. Now, when I rotated this axis entirely by 90 degrees, what we'll have is minus y and x. Abscissa will become minus y, ordinate will become x. Okay. Do you see any change in the length of the vector? No. Why we don't see? When we take L2 norm, L2 norm is nothing but the length of the vector, right? X square plus y square under root. Now here also, if I do it, y square plus x square under root. Okay. So the length is same. What did we change is just the relative position of this point with respect to the origin, right?
Yes.
This is what has happened. So when we have something like here, and we are trying to classify this point and this point, okay, so once a point is on the right hand side, it will become plus 1, and it will become minus 1 with respect to this line. If suppose I took the line and I made it like this, You see the line I just made, this line is like this, then it will not be the same. It will become plus here, it will become minus here, primarily because the position of the vectors are on different sides. Okay,
Yeah.
because the slope is different. Because this slope was minus, right? This slope itself is minus, negative. Okay, and if I try to make it positive, the slope is positive, then of course the relative classification will be different. Okay, I'll try to like give you some idea on this SVM only.
It's okay.
So this is x dash beta plus b. So the beta is the slope of the hyperplane, and b is the bias. Bias is like nothing but some height over the origin. It's not passing through the origin, but the line is somewhere above or below the origin.
Yeah.
Now we will read through this slowly, and then I will tell you which point to focus. So the following problem defines the best separating hyperplane. Find beta and b that minimize the slope such that for all points x, y, y fx is greater than equal to 1. Okay. Now,
Yeah. Okay, person actually, if we go to the other one, I just wanted to know one thing. So like, so here,
here,
yeah. So this, as you said, so minus y is either one or minus one, right?
correct,
And x and xi into w is also one or minus one, right?
correct.
So if minus one and xi w is plus one, it will be minus.
Yeah, that is an error.
Error. Okay. So error means minus. It will be minus. So
Then the cost will be huge.
huge. No, it will be zero only, right?
Why?
It's a max of something. No, it's mentioned max. So this is my actually my doubt actually there. Like
This term will always give us a positive value. Understand? This term will give us a positive value only,
yeah, because
which is why
okay. So like positive value. Okay, minus. Okay, y is one
minus
and
is written because it will give a positive value.
yeah, because
Try and understand.
suppose y is
See,
one.
we know that we have a step function as activation function. So this will become our activation function. Why this will become an activation function is
Is
it will either be zero or
is
something
this not
positive.
like our ReLU activation function?
Forget ReLU. This is not ReLU.
Mm-hmm.
This
Haji,
is
how
not
the
ReLU.
cost function differed for linear regression, logistic regression, and like every regression and classification, how the cost function differed?
See, we have to develop the intuition of cost, not just about logistic or linear or anything. We have to understand that we are trying to classify vectors here. And when we are trying to classify vectors, it can either be in class 1 or class 2, right? So we have to label the classes. Just imagine, okay, within your own scope of imagination. So Manoj can have his own scope of imagination. You, on the other hand, can have your own set of imagination based on what you have read so far. Just try
Mhm.
to imagine on your own scope that if you're trying to label two classes of data, it can be anything. It can be a patient yes or patient no. It can be diabetes yes or a diabetes no. It can be for example, COVID yes or COVID no. Okay, it can be anything, any data set you take it out. So
Mhm.
when you're trying to label out any data and you're modeling your prediction model, you're writing your code for the prediction model, so to classify the binary classification such that it should give you least error. Okay, it cannot be accurate, it should not be accurate because we know it will overfit on the unseen data. We have to be generally close to the problem so that there is minute error. Okay,
Mhm.
so when we are talking about labels, we either talk about 0, 1, okay, -1 +1. Okay, just learn it by heart. It can either be 0 and 1, or -1 and +1. Okay, nothing else. If there is anything else, we will discuss it separately. But this is the history how the machine learning started for binary classification. They took either 0 and 1, or -1 and +1. So perceptron deals in -1 and +1. And why does it deal in that? Because this entire cost, this hyperplane, what I told you, no, when you um, take the take the Cartesian coordinate and rotate it by some angle, okay, then the point itself changes. Like in the 90-degree, when I did 90-degree rotation for the initial Cartesian plane, the x and y interchange their position, and the the x, which was initially the abscissa, got a negative value and got replaced by the ordinate. Sorry, I'll have to share this. Yeah. So the initial vector was x and y. This is abscissa. X is abscissa, y is an ordinate. When I rotate it through a 90-degree, they swap the positions and become negative. The abscissa becomes negative. Okay. So the same thing happens if I, what if I did, I rotated it with 90-degree, and I also translated it somewhere here. Okay. Then what happened? They both will be negative, right? They both would have become negative. Why? Because this quadrant is this would both won't be negative. If I translated it here, now both of them will be negative. This is origin. I have rotated it 90 degrees, and I have brought the point here where the x is also negative, y is also negative, right? So what I basically did is I tried to, if I could not classify the point with respect to this frame of reference, initial frame of reference, I did for my own benefit, like to ease my job, I just changed the frame of reference so that I could calculate better. The same thing happens when we get a data set and we are asked, okay, dear, we just normalize these vectors within 0 and 1. Remember something, whenever you get a data set, you always normalize, use min max scalar, right? You use standard scalar. Why do we use it? Because all these points in those features, like a data frame is a rectangular matrix only, no? So every feature has data in it. So every feature will be normalized so that every vector which we have here can be represented from origin, not from any random point like this. We have to bring this position to the origin. Am I making sense? I mean, can you visualize it somehow? I'm sorry, I don't have this writing pen and all. It will be better if I could write it smoothly, and it was. Hmm. But you get the point, right? If I have a vector somewhere here, this classifies a person with COVID. Okay, this is a point where the person is labeled with COVID, and the vector is here. I don't know how to classify this vector. This vector is somewhere randomly here. If I normalize it, what will happen is it will bring it to the origin. Okay, and there is some person with vector this, and this is not COVID. Okay, if I normalize it, it will come down here. Okay, so I get a smooth plane to separate them. Every person here will be not COVID. Every person here will be COVID, right? Correct. So this is how we label it. Now coming to the initial question, why we are doing this minus? Minus is nothing there, but how we see it, y into fx is 1 is the generalized function. If we are classifying something which is on the, if we are classifying something which is minus initially as plus, what will happen here? I'm classifying this as plus, but it is minus. What will happen? This is an error, no? Hello?
Yes, this is an error.
Correct. This is an error, right? And if something which is plus and I'm trying to classify it as minus, this is also an error. So if I multiply this predicted value with the actual value, sorry, this actual value with the predicted value, and this actual value with the predicted value, what I get is a term which is negative in itself in both the cases. Correct? Yes or no?
Yes.
Correct. So now when I tell you, then whenever you get negative in your function, in the prediction function, if you are getting negative, then my model should be penalized and it should reiterate to find those weights which where it can get positive only. Okay. So for example, if this is negative and I predicted it as negative, then multiplying those I get positive. So I would say, okay, my model has done a good job in predicting a negative vector, and if there's a positive vector and it says it is positive, then multiplying these two will also give me positive. Then I will say my model has done a good job in predicting what it is for a positive class label. Now, the difference is how much distance is it? That is the norm of the vector. So we divide it with the norm and we find the direction. The direction is okay, but you'll have to work it on the distance of the error. That we will discuss separately, but just know that we are adding this minus to tell you, to tell the model that okay, we have to do the positive values only. We do not entertain any negative values. And how the negative error comes? If a positive label is classified as a negative error, like a COVID positive person is given the label of negative, COVID negative, then it will not work, right? So the model will reiterate in itself. Okay. Why? Because this value itself will become negative. Am I get um, am I clear to you guys, or should I explain in any other way so that you can get the intuition behind this? See, this is nothing but a simple cost function written like this. This is max of 0 and this, because it is a step function, nothing else. It could have been an MSE also, like mean square error also. There is no harm in it if we write it as a mean square error. But we write it as a step function. That is why we have to write it either max or this. So this is either 0 or a positive value, nothing in between. Am I clear? Any doubt, you can ask, please. I have
Can it
lots of
be
pictures
a
to share.
negative one here? Zero
Sorry?
or some negative value?
Sorry, please
Why
come
can't
again.
why can't it be a negative one?
Why can't it be a negative one? Right. Because if we have a negative value here, okay, so imagine a child, and we are conducting an experiment with the child. The child likes good sweet or chocolates, right? But we are training the child so that he or she doesn't take toffees or chocolate from strangers. Understood? So how will we teach them? So you a child likes chocolate, but if a chocolate, a bowl of chocolate is kept in front of him or her, and you tell him or her that okay, dear, don't eat the chocolate until I am around you. Like you can see me, I can see you. You don't eat the chocolate otherwise. If you don't see me around, don't eat the chocolate. So you put that chocolate in front of him or her, and you go outside just to see whether he or she will eat the chocolate or not. If the child has learned better, he or she will not eat the chocolate. That is, it will be a positive value. Okay, that's a positive trait. He or she has learned. But if the child picks up the chocolate and eats it, despite prohibiting him or her, saying that it is not good, it is wrong, you should not do it, but still the child picks it up and eats it, it is a negative trait. Do I want to boost up the negative trait? No. What do I do? I'll come back and I will tell again that no, you have done it wrong. You should not do it. You should not ever do it. Maybe incentivize the good behavior and say and penalize the bad behavior in any way. I don't know which way, but okay, we will penalize the way if he or she has done the mistake. Okay, so we do not have negative value just because we do not want to promote it. So if the function, if this function 0 and this value, we don't take negative value because we do not want our perceptron to take on any negative value. Negative value as in, if the function, if this value is negative, then it will be multiplied with a negative here, like this negative value. If the, like this is y only, no, this ai is the sample point, is -1. If it is negative and it's multiplied with minus, then it will give me a positive value only. If it however gives me a negative value, then what I will know, the data point is not wrong because the data point is constant. My value, the slope value is wrong. Why? Because the z is on the plus side and I'm trying to classify in -1, or the w is on the minus side and I'm trying to classify as a plus point, right? So in either of those cases, the value of the function will be, the value of the function this will be minus, and I don't want that. I hope made a little progress on the intuition, maybe. No,
Yes.
somewhat, right? Not fully, but there's somewhat I am able to convince you with the why we don't go for the negative sign and why we have this minus sign here.
But still there is chance that it could be a negative thing.
Of course, there, because we are iterating through this hyperplane is running all circles. It will like this, it will be like this, it will be like this. Any possible orientation it will have, it will take. But for
Okay.
every data point, for every data point, like this point, this point, this point, I'm talking about the data set. This is the data frame, and for this point, this sample, we will try to iterate after every sample. We will modify the weights after every sample. So the hyperplane, if it is initially this, it won't just randomly circle out to this. It might take a small theta, then again a small theta, then some bias here. Then it will try to get me a proper hyperplane which will classify the plus points and the negative points. The final hyperplane will be after all these iterations and after the summation of all the m values, and of course averaging it through. Yeah, I hope a little more clear on this. Are we?
Okay.
You have any other question in any other way for the same thing?
No, no. So there is possibility to have a negative thing. So
Of course.
next,
So there's a possibility of having it, like this is a step function. Now we have understood the step function so far. Have we gone through the initial function? I mean, this is not the only function which we have, right? We can have any other function, but why are we dealing in this line only? Is because we are a perceptron basically is something which will work on linearly separable data. Okay, the starting when we incepted perceptron concept, it was because we wanted to separate out linearly classified linearly separable data. So if you are going to classify uh, two data points, two classes, it should not be like uh, it should not be like one point is here, the same point is here, and the same point is here again. It won't be linearly classifiable. Or a better way to see it like this, data points like this. I'm tired of writing like with a finger on the trackpad. And negative points here. You must have seen this kind of data set somewhere, right? Plus around in making a shell, and negative points within the shell. So this is not linearly separable. If you make a hyperplane here, it will be 50% accurate only. Half of the data is obviously there, and half of the data is here, right? So this is not linearly separable, and it's not very good example to work with a perceptron. Okay. So this is the idea why we are not working with any other basis function, and just we are working with a simple plain line function. Yeah. So yeah, mathematically we have this slope and bias. We know the points. We know what we need to find out, a step function to handle our cost. Now what we have here is the parameter updation function. So this W is W new. Okay, this is W old. What we are doing is alpha by 2. Alpha is the learning rate. Okay, then we are subtracting the original function with the prediction function multiplied with the original data set. Why? Because we have to differentiate it with this value. What I told you here, no? This is the original cost function, what we do to update our parameters. Okay, are we still on, like on? Okay. So this is actually the cost function which we are dealing here, the parameter updation model, which I told you in the PowerPoint. Okay, and this is the bias which we will also update in the same way. We don't have to be any genius to find out that this is actually MSE, mean square error formula, because we differentiate it. We find that once this y is differentiated, we will get only the x value multiplying here, right? So we are looking at it, and in every ml equation, ml or cost optimization function. So can we come to the code part? I mean, right now the math part is okay, right? Or do you have any other question on this?
Fine from my side, actually.
What about Tanumila, sir? Yeah?
Yes, yes, too.
Oh, sorry. You, okay, Tanumila, yeah, I got this. What about Manoj?
Yeah, yeah. Let's go to the code part.
Okay. So you can ask any relevant query with this even during the code. Okay, I'm skipping these functions. Okay, I won't be telling about these functions here. I'll first come to the visualization part. Okay, I just
Uh, Instead of skipping, could you can we go with this one?
it's not worth it going right now. I'll tell you the algorithm first, because it's not
I
like
feel like after listening to this one, I feel like there are few more things that we need to understand.
like
And uh, I have gone through some of the. So I have served some things like actually we can do many things using machine learning things. But why comes to the neural network is because there are still few things where it cannot be linearly separable, where some additional things need to be done. So there comes the concept of neural networks. Uh, Something I think we need to learn about input layers, uh, the need for the hidden layers, and something that is needed to be known regarding the activation functions, or the need of that activation functions. And this, I think, this basic step will make understand in
Yes.
parallel with coding. I think it will give more insight because we are completely unaware of these things.
No, no, it's okay, completely fine. I agree with you. But what we are doing, dealing here is the history, how the neural network started itself, right? When when someone is trying to program a neuron, see, a human brain is a very complicated structure in itself, and there is 10 raised to the power 4, 10 raised to the power 5 neuron networks inside a brain, right? Okay, so you can, a mathematician can easily be overwhelmed by this and can say, okay, if I can do so many concepts, I can write so many theorems, why not develop some mathematical model for the brain, so that that model itself can predict those theorems, those axioms, right? A mathematician, a physicist, all have their own aspirations to design and develop a mathematical model of human brain. So far, since we were not in an era where the computation was, cheap like today it is, and it was not very advanced like the way it is, they used to develop algorithms that could mimic the parts of human brain actions. For example, if we were to um, find an optimal way to search something, they would develop a mathematical model. Okay, if we needed to merge something or sort through a list, they would define an algorithm that will give us an optimized way to search through or sort through or merge through the list. Okay, now their aspirations improved. They wanted to design a neuron like how it is in the human function, human brain. So before writing a function or a program to mimic human brain, they should understand the neuron first, because that is the building block. Like how we say we need to start from the basics, so they started from the basics. And what does the neuron do? We know what a neuron does. It has dendrites, it has a nucleus, it has axons, right? Which a part of dendrite will pick up the senses, it will take it through the axons, and then it will go to the nucleus cell, and then it will decide whether to transmit it through or to keep it as such, whether to say yes or whether to say no. Okay, so all the complicated decisions are taken with either yes, no, and a threshold value. So the same thing has been done here. We are developing a perceptron. Okay, when we develop a perceptron and then we go to the hidden layers, why? Because we want to create a bunch of these perceptrons, hidden layers, and all the dense sequential layers in the keras what we see is nothing but a bunch. It will create a bunch of perceptrons which we will call neurons, neural network. And why I'm not going through these first? Because it is just initializing something which we will learn better if we see the visualization first, right? Now, see, implementation of OR gate. Okay, yeah. So what we have here is a linearly separable data. So one point is on the right hand side, the other point is on the left hand side. So we can very clearly see what we were dealing it. hmm, the initial data, after data, right? So what we have here is before training, I took the initial terms as 0. How should I tell? Okay, weights initialize parameters. Okay, weights are like w naught and w1. We remember w naught and w1 for initial weights like this. This is the initial weight w. Okay, What we do is w naught plus w1 x1. W naught, why do we want to add a w naught? It's because of bias. Like how it give you the child experiment. I told you, when a child is given a bowl of sweets, its initial habit, or say initial response, would be to eat it. That is a bias. If he doesn't eat it, then it's a good bias and it will be 0. But if he eats it, the w naught will be 1. Okay, so that is how the thing is. So now we initialize parameters w and b, and then we have our perceptron is forward propagation. X x is an array, nothing special about it, just the 4 points. Okay, 4 points. And we visualize it in the four corners of the graph on the Cartesian plane. Now before training we initialize the size of xy. What we have with the size is nothing special. Just remember this, we will have to discuss it later. Size is given by initialized sizes. Weights, nothing special. Initialized parameter as w0, b0. Okay, nothing special, we will discuss it later. Now what a neuron or a perceptron does is it will try to predict those points. Okay, and we'll have a hyperplane which will separate those points. Forward propagation is what we do even in a neural network, in a dense or any modern day neural network. We do forward propagation and backward propagation, that we already know, right? And on which data set we do? On x and y, right? What do we have as in terms of parameters? We have weight. Okay, and this 100 is 100 times you have to do it. Okay, now after training what we'll have here is result of a, like, do we have a here? Okay, never mind. After training the result a, then the result of w. Maybe this is the a, right? This is the a. W is weights and the bias is b. Okay, so after training a is a series of labels, right? One, sorry, minus one, 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 one. So this one is minus one. Other points are classified as one. Weights are revised. This is point one. Uh, Sorry, I don't really understand this, but we will have to look through the initial codes to find this out. Maybe this is the W naught and this is the W1. Okay, and the bias is minus 0.05, which you can actually see the slope is negative. As I said, if this slope was like this, it would be plus 0.05 maybe. Yeah, okay. Now we are looking at the cost function here. So this cost function you might remember from max of that's a step function. No, cost function we will remember from uh, this part only. This part is the cost function. Okay, only this part. This is the updation part, but this is the cost part. So when we see this function, do we see any square value somewhere? No, no. Yes or no? It's just a linear factors only, right? So when it is a linear factor, the cost function is linear, right? We don't have any curve here. Okay, unlike any other linear regression, logistic regression, other ML models, we don't see these straight cost function. We always see a curve model for this, for the cost function, whereas here we see the linear values dropping through as we increase the number of iterations. Why the number of iterations bring down the cost function is because with every iteration the value of these weights have become better. After one point, see, after classifying one point, it goes into classify the next point. In the meantime, in the meantime, when it is iterating through this point, it already knows that okay, I have predicted it as something which it is not, and I have to improve it. So while up, updating the prediction on this point, it knows it has a better value of the weights and the bias. Okay, and after classifying this point, it will have again a much more better version of itself, and it will have a better weights and bias. So by the time it reaches the last point to predict, it will have a summation of all those weights averaged out so that it can predict it much better with the least error. Okay, so when we are at the last iteration, we are at the least error, the least cost. Okay, because we are doing it step by step. We have said 100 iterations, right? So with every point 1 2 3 4, after every point we are iterating the cost function and we are getting a better value. Similarly, if we had 50,000 points, say 50,000 points, and we update these weights weights and bias using these functions, then what we will have is a stochastic gradient descent, right? Which is what is stochastic gradient descent. After every iteration we are updating our weights. Okay, so now forward propagation. Let's discuss this forward propagation, which is the basis of any neural network. So we have the data. X and Y is just the data. We need parameters, of course. Okay, and the number of iterations is okay. You want to give it or you don't want to give it. It's just a matter of choice. If you can hard code it that okay, I need 1,000 iterations, you can do it within the function. Otherwise, you can give a parameter argument also. Like this learning rate is hard coded here, 0.1. You could have given it here as well, right? The cost history is nothing but some empty list. We will come to this later. All these things are not very intuitive. When once we write the function and we need these values, we go on adding these variables as on the go, and then we arrange them in an order which is easy to understand. Okay, so learning rate we know, we need parameter we know, iterations we know. For loop, of course, when we are working on iterations, we will of course go for the loop. So for I in range I 1 to the number of iterations. This, however, you know this dot function, right? What is it? Anyone? I hope you have not slept through. Guys, you there?
Yes, dot.
Yeah,
I know it is very boring, and to keep on listening, you might fall asleep. Can you please help me with this? You guys know this dot, right? NP dot.
The multiplication of weight and the input.
No, it's not just multiplication. What it does is
Dot product.
dot product, the inner product of two matrices, okay, or two vectors. So if it was just a product, what it will do if you have say we have a matrix like this. This is M cross N. How do you say we make this matrix? By multiplying vector 1 cross n, okay, with the vector m cross 1. right? Are, are you with me here? I mean, we can,
Yes.
of course, multiply a vector m cross 1 with 1 cross n and get a matrix m cross n, correct?
Yes.
But there is a way we don't get. If we do the dot product, we won't get this matrix like that, do we? If I multiply,
Single line, like single row only we got.
we will add all those, no? So say m cross 1 and 1 cross 1. If I try to multiply this, one row one column, one row one column. But
Mm-hmm.
if I multiply this vector as 1 cross m, just the transpose of it, if I multiply like this, what do you think we get? Like, we get this multiplied by this, we get a single value here. Okay,
Yes.
we will
Mm.
get a single value, right? Because
Yeah.
this first element will get multiplied with the first element plus the second element with the second element in the second row, third element with the third element in the third row, right? And we will get single value. This is the inner product. What we are doing here is the cross product. That's why we get the m cross n product. So here we don't want a cross product, we want a single value, that is x and w, the weight, the theta, we can also call it the w as theta. Theta transpose x we want to do here, plus the bias term. Okay, now what we have here is the sine function. What does the sine function do? Do you remember the sine function? We have used it somewhere before. Where did we use the sine function? Any relevance with the respect to ml? Hello.
Yes. Sigmoidal function only we can remember. What is the sign?
Sigmoid function used it, yes, but how did we use it? We made a s like this, no? We made an x like this,
Yeah.
right? And then we started classifying the model when we get
Mm-hmm.
this, right? We had another problem where we use sine. Okay, the model is right here, neural perceptron. This is the sine function, right? We see here, if this is positive, z is positive, then the value is 1. If the z is negative, the value is -1. The sine function does the same thing. Okay, np dot sine gives me, if the value is anywhere negative, it will give me -1. If the value is anywhere positive, it will give me +1. If the value is 0, it will give me just 0, nothing else. Okay.
Oh,
Hmm. So with respect to perceptron, we are using it. Now product, this cost cost function, this is okay. So np dot multiply a and y. What is a here? The sine function, right? The sine, this sine, the minus y x w, we are doing it right now here. Okay, np dot multiply a and y. Okay, then maximum. What is maximum? This is the maximum, 0 or this value. Okay, maximum is this product and 0. Find any one of the two, whichever is maximum. Now the cost is this summation. We find out the maximum, then we do a summation, and then we take the average out of it. So np dot sum maximum into -1 by m. Why we added -1 by m? And we could have done it here also, but we didn't do it. We just added -1 because we have to minimize it. Overall overall target is to minimize the cost, maximize the profit. Okay, if we suppose say this is an objective function, like in artificial intelligence we have objective function, no, heuristic objective functions, right? We were maximizing them. So we would use minus 1 here. We would have kept it as positive. But since it is a cost, we will try to minimize it. And how do we minimize something? We take a negative of this value and then we maximize it, right?
Mhm.
Are we clear? Yeah, and
Yeah.
one more thing in relation to this is whenever in mathematics we are talking about optimization, whichever gradient the we are using gradient only, right, to maximize to optimize something. So this gradient is basically targeting the positive side. It maximizes something. Whenever we try to use the gradient technique, it will only maximize the function. So whenever we are talking about cost, we add the minus term deliberately so as to do a negative gradient, which is why we say the gradient descent and not gradient ascent. Okay, so this is the same thing. We add the minus term deliberately so as to minimize the cost. Now, this squeeze the cost, I don't really know how it works, but let's say we will revisit this entire line somewhere down the line. Okay, cost history, append cost. Okay, okay. So after every iteration, it will just impute the cost incurred to this list one by one. Okay, it's not a very good way of handling, but it's very intuitive, nicely written. Okay, now updation. Okay, so this formula is represented here. I think you can understand it. Learning rate is the alpha. Okay, alpha by 2. W is the initial weight which we had before starting in the parameters. Okay, so the W minus learning rate by 2 into the dot product of X transpose. This is X transpose. Okay, and A minus Y. This minus Y. And for the bias term, we have learning rate by 2 into NP sum A minus Y. A minus Y. Okay. So we know that, right? This dot T is a inbuilt function for transpose of any vector. This is the same term as this. Okay. X dot T. You can write it here also, but okay, we have written it here. Not a problem because ultimately we are taking a dot product. So what we have here is a forward propagation where we have xy weights as the parameters and 100 iterations. After every weight iterations, we are
Why are we using here x dot t?
that is what I told you. No, x dot t is nothing but this term. When we are multiplying a vector, see, um, target is always a column, right?
Hmm.
Imagine a data frame now.
Yes, yes, yes. Target is always a column.
Yeah, and the predicted value is also a column.
Yes.
Yes, and
Hmm.
now I have to multiply it with the data. Data is a row.
Okay.
Data is row, like all the x's,
Hmm.
right? So what I told you here is like I have to multiply it this and this, right?
Yes.
So earlier x was this, y as this, or you can say x as this, y as this. Okay. Now you have to multiply to get a single value. So you take a transpose, you do it. Okay. You take one transpose and you get the product. Let me tell you in other way. Okay, this is not very
Uh,
intuitive. I'll tell you. I'll just how do I get
Suppose if we are having a real time data size, that one,
yes.
um, can you explain that data in the terms of the matrix sizes here?
Yes, which is what I'm trying to do. I was just looking for the mouse actually. But hmm, so this I'm not writing it, but this is the target. Okay, and this is the data frame. Okay, a structured data frame, well structured. It will have features here. It is feature one, feature two, three, four, five. I have five dimension to this. Okay, and this is the target, a single column y. Okay,
Okay.
now for every set of data, for like sample one, the sample one is in the row one, right? Please put the mic on only, no? You say yes or no after I speak.
Yes, 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 yes. And the mic
Good.
is on.
Okay. So we have a sample one here in the first row, and after I see the first row, I see that there are five dimensions to it. Like I have
Yes.
to instead of three dimension, I'll go in the five dimension, which is hard to visualize, but you get the idea already. If I was using these three dimension, I would have taken a Cartesian coordinate like this and define a point here. Okay, but
Okay.
just because I have five features, it is difficult to visualize. But just say I have two more axes and I define some point here in the plane, and then I say, okay, this is the y value. Okay, so all these values which are in these features will give me a vector like this, and it will point to a single y. Okay,
Okay. Mm.
now what we have here is we have to normalize it. Of course, whenever we are given a data, we normalize it to bring it down to 0 and 1 range. Okay,
Mm.
right? So
Yes.
after we do it, we try to predict. Okay, and
Okay.
when we try to predict, what we have here is error, of course. So now I write a different column. It will be my predicted values.
Okay.
Okay, so y hat. So now when I see I have the data, I cannot change my data. Okay, I can change
Ah.
only my y hat. So
Okay.
whenever I see a data and I try to predict the y hat, it goes like this.
Okay.
So
If
I
it
know,
doesn't matches.
yeah, if it doesn't match, and it should not match, otherwise it will overfit, right? So this
Okay.
difference I will have to minimize, just
Mm.
minimize, not make it zero. Okay. So
Mm.
what I will do here is, your question was why we are doing X transpose, like why we are doing this into this. Okay, this is done because we have a point which is wrongly predicted and we have to classify it correctly. This is the error, and this we have to minimize it. So how do we minimize it? By using a function this. Again,
Okay. So a
just
minus y there can I consider as a is the actual and y is the
of
predicted one
course, yes, yes, yes. A is the
from
actual one.
code. Okay. So
So
both are vectors.
the both are vectors,
Multiplying it matrix.
right? So this is the, what is this? We are using an MSE, mean squared error, right?
Okay.
Now, how do we solve this one? This is a quadratic function, right? This we will not solve as such. We will do a differentiation. Okay. We will differentiate it with like partially differentiate it because we have y hat as theta transpose x. What is theta transpose and what is x? X is the data which I cannot change. Theta is something which I was iterating, like the first feature multiplied with theta 1, second feature multiplied with theta 2. So just to tell the model that okay, the first feature is theta 1 times important. If it is 3, then it is 3 times more important than theta 2. Okay, if theta 1 is 3 and this is 1, then it will just say that the feature 1 is 3 times more important than the theta 2 feature. That's
Okay.
it, right? So we can write the y hat like this. Ultimately, we will solve this function with the partial differentiation and we will get a term like this.
Okay.
Boils down to this every single time. Every single time it boils down to this. So when we are writing y minus theta x, what do we have it here basically? Is a scalar point, right? This is a scalar thing. It's not a vector anymore, right? And what do we have here is a scalar thing, not a vector anymore, do we?
Okay. Mm.
But when we are writing this in terms of an entire data frame, we see that this is still a vector and we
Mm.
have many vector operations here, right?
Yes.
The a, we are, this y is the a and it is still a column. We have to work on the entire column. Computation has to be performed,
Okay.
right? So how do we do a multiplication of a vector with another vector? We cannot multiply a row vector with another row vector. Can we? We don't do that. We cannot do it because it is impossible to do it. But we can do it. We have to devise a way. We can do it either by transposing this vector or the second vector. So the efficient way to do is transpose the first vector and then do it with a column vector. This is the efficient way, which is why we do a theta transpose x and not the other way around. Okay, this will take some time to absorb um, if you can take my advice. Just spend half an hour to 1 hour on linear algebra every day. It will build
Okay.
your uh, intuition of why we are doing like this. Okay, because I every time keep. Okay. So I didn't even realize it's 11:30. I hope I'm making sense in whatever way I'm talking. I'm not very sure you guys absorbing it completely, but even if it is partial, it's a good thing. I mean, I will try to encourage you to go and read books on linear algebra. Please do it because everything I'm telling you is about linear algebra only, and everything in future, whichever way you are doing the computation, is about linear algebra, linear dot products, cross products. All these are about linear computation. Okay, and the point which we were before this meeting was off is here. When we compute an entire data frame, it is nothing but a matrix and a column. Remember how we do the train test split? You remember that, right? We take that x and y we split it. We take the x's out and we take the y's out because internally we know that even if it is shuffled, like randomly shuffled, it will Like this is the x part and this is the y part. Even if it is randomly shuffled, when we concatenate these two matrix, we will get each data corresponding to the y data. Okay, so which is why linear algebra comes into play, because we have to use operation on every single sample. Say if it is 50 or say 50,000, we will always find a way to relate these five terms to a single point here. It will not happen any point of time that this point is being mapped to some point here, unless until it is duplicate values. Okay, am I making sense?
Yes,
Yeah, please.
actually, um,
uh,
can I?
yeah, please tell me.
Suppose we are having here five samples.
How many
Okay,
samples?
five
Okay, five samples. Yes.
or something like 10 with five different features
Okay.
and with one target value. With um, so this 10 by 5 is my matrix size for the x vector. Am I right?
No, you have five samples, you say, no?
No, 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 10 samples.
Okay, 10 samples and five features.
Yes.
Then the x vector, the x matrix will be 10 by 5. You are correct. Yes.
Okay, this is 10 by 5
Yeah,
and the y the target will be 10 by 1.
10 by 1. Correct.
So x matrix I have got 10 by 5, y matrix I got 10 by 1.
Hmm.
Then how can I get this weighted matrix?
Yes, but that we are talking about x and y only. Where is the theta matrix?
Yeah, I'm asking the same thing.
Yes,
Where is the
exactly,
theta
exactly,
matrix?
exactly. So this y vector, we are 10 cross 1. We will use it, but not now. When we will use it? After we find the relation, like um, out of this 10 cross 5, okay, I am taking out just 1 cross 5, okay, out
Okay, for
of
single sample. Okay, 1 by
single
5.
1 by 5. I'm taking out 1 by 5. Again, in the second iteration, I will take 1 by 5.
Okay.
Third iteration, I will take 1 by 5.
Mm.
Fourth iteration, I will take, and up to 10 iterations, I will keep on taking one sample each time. And I'll do.
So,
Uh,
sorry to interrupt. If we
no, no.
go with the code,
Hmm.
um, there you have mentioned the iterations now. That is those iterations and that here iterations the same?
Where where are we talking about this?
No, no, code, Python code.
Yeah, in Python code. Okay, yes, this one, no?
Here we had iterations, no, in the for loop. We are having here
Forward
I,
propagation.
somewhere we have
Forward
here
propagation, no?
iterations,
Yeah,
x, y parameter and iterations. It means
correct.
that this okay, these iterations
With
means
that
we are going sample by sample.
sample by sample, yes. Which is why the dot product, not a simple multiplication. We have a multiply function here, no? We're not doing a multiplication here. We are doing a dot product. And what does a dot product inherently does is it will take a transpose of the y automatically, or the
Yeah,
w
coming to
automatically.
that point only. If we go to that notebook thing where you have drawn the matrix, no?
Yes.
Yeah, this one. So 1 by 5, and this is 5 by 1.
No. This is 1
1
by
by
5.
5.
This is
Okay.
1 by 5. Okay. And what is this? This is 5 cross 1. See,
How 5?
theta is the weight. See, here we are taking dot product of weights and the excess. After I say my machine learning model that, okay, dear, if I say the name of the machine learning model is Z. Okay.
No, no,
So
no. Actually, Prasun, I was asking like, see, in our when a data is given, we are having only samples, features in the target variable. We don't know the weights
of course we don't know weights, but we will initialize it, no, with all one.
using some rand function. Or how are we
Mm,
getting these weights?
it can be a random function, but we don't use a random function. We started with all one single. Why do we use one here? Because we are of the impression that all these features are linearly dependent on each other. What do we mean by linear? What do we mean by linear? We mean that all the terms, when we add with their power as one, we will find the target.
Relationship with the target.
Yes,
Okay.
right. So
Okay.
we initialize them as one. Now, once I see the coefficients, by using the one as coefficients is not doing me anything better, and the error term is high, I will iterate it again, and I'll update the weight as per my understanding. But whichever error I got, maybe this will go to zero point 0.5 and this will go to 2. Then
On that same sample, first sample.
yeah, after the first sample is calculated, the first sample is calculated with the coefficients 1 only.
Okay. If I
Yeah,
get some error term, then I'm going to do
update it
some
in the
updation.
second. Yeah, update
Okay.
it in the
My
second.
weights get updated.
Correct. And how do we update it? Because we are multiplying this theta with the x, with the dot product. This
Okay.
theta with the first sample as a dot product, so that we get this theta 1x1, theta 2x2, theta 3x3, theta 4x4, theta 5x5.
Okay.
Right. Hmm.
So
And
features are now associated with weights.
sorry.
So now features are associated with the weights.
Yes, we associate the feature with weights. We do, but initially we assign the value as one, just because we don't know it yet. Like what value should be
Okay.
assigned?
Okay. 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 Got it. So no, no. How this transpose?
How this transpose? Like say, if I want to, um, you remember that we always try to use an efficient data structure to make our life easier, right? In computation, what we
Okay.
can do is there is one way to do it. Like I can say a list of theta 1, theta 2, theta 3, theta 4, theta 5. Okay, and I have a sample x1, x2, x3, x4, x5. I can do a loop and then nest it with another loop and then say, okay, multiply theta 1 with theta 2, then go to theta 2 and then multiply x2, like that. But do you think that is efficient? Like the asymptotic notation, what will we have there? N square, right?
Yes.
Which is a like
Mm.
polynomial
Okay.
polynomial way, no? Doing. But if we multiply theta transpose x, a vector operation, which is a CPU operation, a CPU can perform this matrix operation, right? Theta transpose x. It's not a big deal. So if I write that way, then it will not take that much of time and space to do it. It will know that we have to transpose it and then multiply it, and it will give me a value in at one go. It's just it will multiply its
Oh,
corresponding values and give me a
okay.
value.
So this is what you are trying to tell me, like, see, X we are having for single sample 1 by 5.
Yes,
Thetas also we are having 1 by 5. But
yes,
our target we are comparing only with the one value, which is a scalar.
correct.
So we cannot simply do the multiplication of 1 by 5 into 1 by 5.
No,
So
it's
you
not
are
possible.
trying.
We
So
need.
we are, yeah, yeah. So we are trying to transport either of any of the matrix
Hmm,
instead of transposing the features in order to not to disturb the data original thing. We are trying to transpose the uh,
No, to make our
weights.
completion easy, yeah, we